All right, everybody, good morning. Welcome to the last day of a lecture. Hope you guys are gearing up for a good finals week here. Two quick announcements. I realized this morning on my way over here that I have not heckled you at one time even for to fill out your SEI. And I also haven't seen the numbers of who has filled them out. But please do fill those out. They're important for all your classes, and I'd really appreciate your feedback on the course. And please be honest. Yeah, that's I use those to improve my teaching, hopefully, in the future. So please do complete your SEI. Vanessa just asked me a question. I changed my mind. I am going to have ops hours on Wednesday. So the tutor room... are there finals on Wednesday? There are finals on Wednesday. Okay. Then my ops hours will be in their usual place. Never mind. I was thinking tomorrow's the reading day, right? Not Wednesday? Is that right? Okay. So my ops hours will be in their usual location and time on Wednesday. Never mind. Yeah, I have your homework 8 to give back to you, as well as any other homeworks if you haven't gotten those back yet. So come see me afterwards. And today we're just going to spend a little time doing some review. Before I do that, any questions or comments about the final or anything else? Okay, well, I sent out that email yesterday, so coverage is officially 7, 8, 9, and 12, with that last little section of section 13.1, which was at the end of the chapter 12 notes, is officially on there. Usual format, bring a note sheet front and back. One piece of paper front and back would be great. Calculators are fine. Please no cell phone calculators. All the usual stuff there. We'll be in here 8 a.m. on Thursday. One more 8 a.m. period, right? Why not? Okay, well, hopefully you've had a chance to take a look at the review activities. That the final exam review that I posted on Carmen Solutions should now be up as well. I wanted to take a few quick minutes here to just kind of do a rundown summary of what we've talked about in the last part of this class. So yeah, the chapters that are going to be covered on this test, there's a lot more of them, but I think by now we've sort of started doing a lot of the same thing over and over. And so even though there's a lot of material, I think if you guys have a handle on sort of these main concepts, that's what's going to be important on here. So in chapters 7, 8, 9, we talked about doing inference, right? We're in chapter 6, we talked about estimating parameters, and chapter 7 and 8, we talked about doing inference, which was, confidence intervals, hypothesis tests. And there was this general form that for all the confidence intervals we'll see that you'll be asked to do. They're all of this form. So we always have an estimate, and then we add and subtract something, some stuff that we add and subtract on there to our estimate. And that stuff is a critical value and an estimated standard deviation, unless we happen to know what the standard deviation is, and then we don't need to estimate it. And similarly for your hypothesis tests, in at least pre-chapter 12 anyway, everything was of the same form. Our test statistic is our estimate. Subtract off the hypothesized value for that estimate, which comes from the null hypothesis. So this is from the null hypothesis. And then again, we divide either by the standard deviation or the estimated standard deviation, depending on the setting. Or for proportions, the standard deviation there depends on the hypothesized value. So just a few details to keep straight there. But again, it's all of this same form. So taking your estimate, subtracting off the hypothesized value, and then dividing by the standard deviation that's sort of appropriate to that example. And so then your critical values and your p-values again depend on the distribution of your test statistic. So we've looked at cases where that is a t distribution, or it might also be a z, just standard normal distribution. So yeah, it depends on the distribution of your test statistic, which for the various settings we've talked about how to know which is which there. For confidence intervals, always make sure to interpret. So it's great to calculate the correct interval. That's very important, but it's even more important to kind of explain your results and say what they mean. So make sure to say, you know, we're 95% confident that the true blank, whatever we're talking about, population proportion or sample population mean, whatever it is in the interval that you say. So kind of just say exactly what it is that the interval that you calculate, say exactly what that means. That's very important. I'll be looking very carefully at your interpretations there on the final exam. For your hypothesis test, your usual strategy, set up your hypotheses. What's your null hypothesis? What's your alternative hypothesis? Determine or calculate the test statistic. So for whatever the correct formula is there. Then you want to calculate, using the test statistic, calculate your p-value. And then using the p-value, make a decision to either reject or fail to reject. And again, make sure to interpret. So interpretations are, again, very, very important for hypothesis testing. And kind of our usual template is there is. So if you've rejected the null hypothesis, you'd say there is sufficient evidence to conclude that the alternative hypothesis is correct. Or if you fail to reject, there is not sufficient evidence to conclude. And then, so you're always giving your interpretations in terms of the alternative hypothesis. And you can often sort of just restate the question of interest that's in the problem because that's what goes in the alternative hypothesis. Okay? So I know you guys are well, very, very comfortable with this stuff by now, I think. So then it is kind of a matter of choosing the correct test. So are we doing a one sample mean or a two sample proportion or some variation of those? So kind of the first way to figure out which test you need to do is what information have you been given? Do I have a certain proportions, 85 of 216 people have such and such, or am I given a sample mean, or so that kind of directs you mean versus proportion. Have I been given a standard deviation? If you've been given a standard deviation, population or sample, then you know you're going to test for a mean. Is it a one sample? Is it a two sample? And again, it is important. Always make sure to check the conditions that are to make sure that the test you're using is appropriate in the setting. So if you're looking at proportions, we want a random sample, and you need that large enough condition. For means, we need to have a random sample, and then if it's normal, there's some things that happen there. If it's not normal, again, this is all stuff that you've seen before. If you have a two sample, we do also want to make sure we have independent samples there. That's something we need to happen. Okay, so regression is a little bit more fresh, so I didn't summarize it like this for chapter 12. Any questions or comments? I know we've been doing kind of the same thing for the last month in this class, feels like. I realized that I didn't put any questions on the final exam review about type 2 error calculation or that kind of thing, but that is of course fair game. That could show up on the exam. So don't forget how to do that. Okay. Okay, well then I think we can move on to the final exam review. Does anybody have any questions they would like to request to be done, to work through in class here? Yes, sir.
Would you post this on the website?
Definitely. You mean these first few slides here?
Yeah.
Yeah. Yes, I will post. That's a good question. I will post the sort of review slides here on Carmen after class. Yeah. And that's reminding me, I also did not yet post the completed chapter 13, section 13.4 stuff. I will also post that as well for your enjoyment. No requests? Okay. Well, I think maybe I definitely want to make sure to do a regression problem, but let's maybe go to nobody has a request. You're going to make me choose one of these? Okay, well let's start with number 2. Sounds like a good place to start. Okay, so big long text here at the beginning of this example. This is again from your text. So we have quantitative non-invasive techniques are needed to assess symptoms of peripheral neuropathies such as carpal tunnel syndrome. And here we have a test that involves sensing a tiny gap in a smooth surface by probing it with a finger. And this sort of resembles many work-related activities, and so we can use this to sort of assess people's ability in some sense here. Okay, so when we do not allow this finger probing, the sample average gap detection threshold for 8 normal subjects was 1.71 millimeters with a sample standard deviation there. But then for 10 carpal tunnel syndrome subjects, we have a sample mean and standard deviation there as well. Okay, so do the data suggest that the true average gap detection threshold for CTS subjects exceeds that for normal subjects? State and test the relevant hypotheses using 0.01 level of significance. Okay. The font is really big here on this for some reason. Okay, so what test do I want to do here? Let's start there. Yeah, Matt.
A two-sample test.
Two-sample test for proportions or means? Means. Okay, yes, exactly. So we want to do a two-sample test for means. Again, that's just because we have 2 samples. We have the normal subjects and the carpal tunnel subjects. And we're looking at the true average gap detection. So we're looking at an average here, so we want to do something that involves a mean. Again, you're given a sample standard deviation, so that kind of points you in that direction as well. Okay, so let's set up a little notation here. So let's let mu1 be the true average gap detection for the normal patients. And let's let mu2 equal same thing, true average gap detection for the carpal tunnel patients. Okay, and so then we want to set up our hypotheses. We have our null hypothesis and we have our alternative hypothesis. And again, a two-sample test, we're always looking at the difference between these two means. So let's have mu1 minus mu2. Okay, so our question of interest here, does the data suggest that the true average gap threshold for the CTS subjects exceeds that for normal subjects? So what will my alternative hypothesis here be? What does that imply about? What does that statement imply about the difference in means here? Mu1 minus mu2. Greater than 0? Less than 0, I think. Yeah. So we're comparing it to 0 because we're not saying is that difference, more than 10 or less than 3 or something like that. So we're just making a straight up comparison. And again, my question says that. Sort of turn the question into a statement. It says that the average gap detection threshold for the CTX subjects exceeds that of normal subjects, so that mu2 is bigger than mu1 is what my alternative hypothesis says, so that their difference is less than 0. Okay, and so then we always our null hypothesis is always that difference is equal to whatever that number, the 0, is there from the alternative hypothesis. Okay. Okay, well, I guess I left the question on there. Okay, so those are our hypotheses. We have mu1 minus mu2 equals 0 versus a less than. Okay, so what sample, or what do I need to assume here to be able to do this test? What do I need to assume? So as might often be the case, there's not a lot of information given. So it's thinking about what do we need to assume in order to do this test. Yeah, Andrew.
Random independent.
Random and independent, yes. So we need random and independent samples. Very good. And what's the other condition that what's the other assumption I need to make here? Yeah.
For this one, I think it's just that the CTS subjects are normal.
Yeah. So we need to make sure. So why do you? So we need to make sure the CTS subjects are normal. And why do you say that?
Because the other people explicitly says they're normal.
The other people it says are normal. Yeah. So normal, I think we just mean they don't have carpal tunnel. So there's not a capital N on that normal. But you're exactly right. That is what we need to assume. But why do we need to assume that our population distributions are normal? Yeah, Matt.
That's because we have such a small number of samples.
Yeah. So because our sample sizes are both very small, right? So we have 8 subjects in the first group and we have 10 subjects in the second group. So we need to make sure that the gap detection is, for both of these groups, follows a normal distribution because our sample sizes are very small. So I need to assume normal distributions for both of these populations. So for the gap detection, okay. So that's kind of what we need to be because our small samples are small. Okay, so I think in a real world setting, you would have the data, right? You would have information on these 18 people, and you could summarize, look at a histogram, do some various things to check if that's a reasonable assumption. For now, we'll assume that that's okay and kind of proceed with this test. So again, on the exam, I will be very clear about what assumptions you, or if I want you to check assumptions, kind of how I want you to say that. But just make sure that you're saying the one that's appropriate for whatever test you are choosing here. So this is what we need to assume in order for our results to be appropriate or trustworthy here. Okay, so assuming that checks out, let's move forward here. So let's see the information we have here. Our first sample, we have 8 people. Our first sample mean was 1.71. The first standard deviation is 0.53. It's our first sample. On our second sample, we have 10 people. Sample mean is 2.53. Second standard deviation there is 0.87. Okay. Okay. So what's my test statistic here? So if I have a 2 sample for means, and well, maybe it's obvious. Do I know the population standard deviations? No. So what's the letter of my test statistic going to be? Is it a T or a Z? Yeah, it's a T. So when I don't know the population standard deviations, I'll be doing a T test here. Okay. So then, does anyone remember what my test statistic is going to be here? So what's the general form? My test statistic is always my estimate minus the hypothesized value of that estimate divided by estimated standard deviation. Right. So I'm trying to estimate mu1 minus mu2. So what's my estimate for that going to be? Thank you, Kyle. So we have x bar 1 minus x bar 2. Again, what's the hypothesized value for that, for my parameter mu1 minus mu2? 0, yep. So that's from the null. I'm saying that difference was 0. And then the standard deviation for my two sample means is I'll take my first standard deviation, my first variance divided by sample size plus second sample variance over the sample size. Okay? So this is just 1.71 minus 2.53 divided by 0.53 squared over 8 plus 0.87 squared over 10. And that is negative 2.46. Okay. So again, I have a t-distribution here. So what do I need to calculate before I can do the p-value with the t-distribution? Degrees of freedom. That's right. So what are my degrees of freedom here? What's that? Got to do the formula. Yes, right, exactly. It's that messy, horrible-looking formula. So my degrees of freedom, I'm calling a new, which is the first variance over sample size. Well, this would be a good thing to have on your formula sheet. Then we have S1 squared over m divided by m minus 1. Okay, so that's kind of that big mess. And if you plug all this stuff in, you'll get like a 0.0123. That's 300000812, which is 15.15. Okay, so what degrees of freedom will I use? I think I heard it. Yes, 15. Use degrees of freedom equal to 15. So we want to round down when we don't have a whole number there. Okay. So we are finally ready to calculate a p-value, and of course I haven't given myself a blank slide here. Okay, ignore that for the second. So my test statistic is negative 2.46. My degrees of freedom here, I'll use 15. So my p-value will be the probability that a t random variable and then something about negative 2.46. So what goes in there in my p-value calculation? Less than, exactly. My alternative says less than. And so now you go to the table, make sure you're in the right degrees of freedom row, go to the 15 degrees of freedom, and pick out something that's close to negative 2.46 to find what your p-value is. So from the table, the p-value that you will get here is approximately 0.012. Okay. So so I have test statistic, p-value, then what's my next step here? Yeah, right. So I want to either reject or fail to reject, and I do that by comparing. Jamie, you said how do I make that call?
Compare that.
Yeah, compare your p-value to alpha. So what is alpha here? So if it's not stated, you'd use 0.05. Ignoring that, what's on the top of the slide currently. Here, the alpha that we want to use, we want to compare this to 0.01. Okay? So p-value it's very close, but p-value is bigger than alpha. So therefore, what's our decision? Fail to reject. Does anyone want to try to interpret that for me here? What is failing to reject a null hypothesis? What does that mean? Yeah.
There's not sufficient evidence to conclude that
Yep.
the hypothesis is or the other one is correct.
Yeah. So there's not sufficient evidence to conclude, and then you want to say the alternative hypothesis sort of in words. So there's not sufficient evidence to conclude what?
The difference between them is less than 0.
Yeah. So there's not evidence to conclude that the difference in the mean between my two groups is less than 0, and I should say which group is which, right? So that there's not evidence to say that the mean of the normal subjects is less than, is less than the carpal tunnel group, right? And so it's good to reason through that, but you can also kind of go back to what is my question of interest. So my question originally said, do the data suggest that the true average gap detection threshold for carpal tunnel subjects exceeds that for normal subjects? And what we just said is that no, there is not evidence to suggest that the true average gap detection threshold for carpal tunnel subjects exceeds that for normal subjects. So if you're struggling on how to interpret the alternative, go back to your question of interest, and there's your interpretation. So there is evidence. So if we had rejected, we would say there is evidence to conclude that the true average gap, et cetera, et cetera. Since we failed to reject, you would say there is not sufficient evidence to conclude that the true average gap, et cetera, et cetera. So I won't go about writing all that down, but that's kind of the right idea. Yeah, Dan.
In the question, when you ask for us to state the relevant hypotheses, do we actually have to write down the words of the hypotheses, or is it just sufficient to write HO and HA?
Yep. So the question was, like here, I ask you to state the relevant hypotheses. Symbols are fine. Symbols are fine. Yeah. I think in chapters 8 and 9 it makes more sense to use symbols, and so if that's what you're comfortable with doing, that's fine. In regression, I think sometimes words might a hypothesis that includes words is fine too, but using symbols is probably the more straightforward way to do it. Yeah. Okay. Any other questions on this problem? Okay. Did anybody come up with a request in the last 15 minutes? Yes.
Something from chapter 12.
Something. Yes. I was going to move on to chapter number 7 here. Okay. Let's jump ahead to number 7 here. Excuse me. All right, so here we have, we're talking about wastewater. So in biofiltration here, air discharge from a treatment facility is passed through a damp, porous membrane that causes contaminants to dissolve in the water and be transformed into harmless products. So we have data here on X is the inlet temperature, and Y is the removal efficiency percentage. That was the basis for scatter plot that appeared in this research journal here. Okay, so we have our two variables here are temperature and the removal efficiency for this. And as usual, we're trying to we'll set up a simple linear regression model here to kind of determine is there a relationship, or what is the relationship between these two variables. Okay, so part A, giving you an analysis of variance or an ANOVA table here. And kind of like your homework problem, we want to complete the table. Okay, so there's 1, 2, 3, 4, 5, 6 things to fill out here. There's no mean square for the total or anything like that. So let's start over here with my degrees of freedom. What will my model degrees of freedom be here? Just 1, right? So, and then my total, yeah, right, just add them up, right? 31. So, again, if you kind of imagine there's a summing line here, the sum of squares, the degrees of freedom and the sum of squares column will add up there. Okay? So then, I didn't tell you this, but how many observations do I have? 32, right? So this is your total degrees of freedom is always n minus 1. So your sample size is 32. That's not overly important, but anyway, what would the sum of squares for my model be? Yeah. So how would you get that number? I guess. Yeah. So my regression sum of squares here, my model sum of squares is equal to the total minus the error sum of squares, which here is 2.7786, thereabouts. Okay. How do I find my mean square? My mean square for my model and for the error? Yeah, I just take my sum of squares divided by its degrees of freedom. So I take, so here I have my sum of squares divided by degrees of freedom. So 2.7786 divided by 1 is 2.7786. My error, mean square for error, again, 0.7223505 divided by 30 gives me a 0.0241. Okay? And then what's my F ratio? Or how do I calculate my F ratio? Or my test statistic here for if I'm doing an overall F test? Say again? Yes, exactly right. So this is my test statistic, which is my mean squared for regression divided by the mean squared for error. So that's just 2.7786 divided by 0.02. I get a giant F ratio, 115.398. And then my p-value there would be 0.00 or less than 0.0001. Much less than that, actually. Okay? So again, the ANOVA table is kind of set up so that once you start piecing them together, first start with your degrees of freedom and sum of squares, and then everything else is calculated from those first two columns. So that's how all that fits together. Okay, part B here, keeping your eye on that ANOVA table. What is the proportion of variation in removal efficiency? So that's my y variable that is explained by the linear regression model with inlet temperature. So what am I asking you here for? R squared, exactly right. So again, remember our interpretation for R squared is that's the proportion of variation in our y variable that's explained by the linear regression on x. So anytime you see that proportion of variation, you're thinking R squared. How do I calculate R squared? Based on the sum of squares. Anybody remember that formula? Andrew?
SSR over SST.
That's right, SSR over SST. So SST is sort of my total variation in y, and my SSR is the amount of variation that's explained by my regression model, so that's why we have a proportion of variation going on here. Anyway, this is 2.7786 over 3.501, thereabouts. So 0.794, or about 79.4% of the variation. Is that good with everybody? Okay. So using the overall F test, is there a significant linear relationship between inlet temperature and removal efficiency? Okay, so let's set up what our hypotheses are here for this F test, and then go forward there. So what's my null hypothesis versus what's my alternative hypothesis? So here's an example where if you want to write the hypotheses in words, or if you want to write it in symbols, either one is okay. Okay. So let's start with the alternative. That's usually a good place to start. So what will the alternative hypothesis say, sort of in words, based on the question here in part C? What will it say about there being a significant linear relationship? Yeah, so before we get there, so these hypotheses, they will both say something about there being or there not being a significant linear relationship between my variables here. So what will the alternative say? Will it say there is or there is not a significant relationship? There is a relationship, right? Yeah. So my null will sort of be that there's no relationship between these variables. My alternative is that there is. So sort of in words, you can think about it as the null says that there is not a significant whereas the alternative says that there is a significant linear relationship. Okay, so if you want to write your hypotheses like that, that would be perfectly fine. How would we write these out in symbols? So how would I write my alternative? Let's start with my null hypothesis. How would I write that out in terms of symbols? So both of these will involve the expected value of my y variable. So maybe let's start with the alternative. So if I'm saying there is a significant linear relationship, again, between temperature and removal efficiency, what would I expect my y to be a function of as a function of x? Beta 0 plus beta 1 x. Okay, so that means that the relationship between x and y is in fact linear. Or the relationship of what I expect my y variable will be a linear function of x. On the other hand, what will my null hypothesis say then if there's not a significant linear relationship between y and x? It'll just be, so it's just equal to a constant as a function of x. So you can sort of imagine that I'm adding on 0 times x. So I'm saying there's no linear information in my x variable as far as the y variable goes. Okay, so again, either way you want to write out those hypotheses, totally fine. Okay, so those are my hypotheses. What is my test statistic? What letter will it be? It's going to be an F. I'm doing an F test. And again, I go back to my ANOVA table to figure out what my test statistic is here. It's the mean squared for regression over the mean squared for error. So that is which is 115.398. So yes, sir.
Going back to the hypotheses, if we had just put beta 1 equals 0 and beta 1 does not equal 0, would you have accepted that?
Yeah, so going back to the hypotheses, if you would just put beta 1 equals 0, beta 1 not equal to 0, I think I'd rather you put it in terms of this. So beta 1 equal to 0 versus beta 2 not equal to 0, that's when we're doing inference specifically on the beta 1 parameter. So the overall F test is answering is answering these questions over here. So is there a significant linear relationship? And so the hypotheses here a little more formally say that either yes, there is a linear relationship, or no, there is not a linear relationship. So if I'm asking you to do the F test, either write it in words like there, so there either there is not or there is, or put it in terms of sort of what your model is. Is it just a constant as a term as a function of x, or is it a linear function in terms of x? So for an F test, don't just say beta 1 equal to 0, beta 1 not equal to 0. Again, here in this case, that's sort of an equivalent. It's kind of getting at the same thing, but in a more general case, these would be the hypotheses that you would want to say, not just talking about one of your parameters there. Good question. Yeah. Okay, so that's our test statistic, our p-value. So maybe, sorry, let me go back to that question. So again, there's two ways that we talked about testing if there is a significant linear relationship. So if you're doing a t-test to answer that question, you would do the beta 1 equal to 0, beta 1 not equal to 0. If I'm asking you to do an f-test, then these are the hypotheses that you'd want to do. So because I'm asking you to do the f-test, say something more than just beta 1 is equal or not equal to 0. Okay. So anyway, my p-value again comes from my test statistic, but we can pull that out of the ANOVA table. So there's your p-value there. So it's going to be less than 0.0001. So therefore, what is my conclusion? Reject or fail to reject? Reject. So therefore, reject the null hypothesis. And again, what does that mean? Well, what that means is that what does that mean if I reject the null hypothesis? Exactly right. So that means that there is a significant linear relationship between temperature removal and efficiency. And formally, we'll just say again, there is sufficient evidence to conclude that there is a significant linear relationship between inlet temperature and removal efficiency. Okay? Good with everybody? Okay, so here's some, I got squished on top of the text, sorry about that. So here's some additional jump output. Here's your parameter estimates. So the question here is asking us to interpret the estimated slope parameter and provide a 95% confidence interval for beta hat 1. And then does our answer, does our confidence interval support the results from part C is the thing that you can't see. So what is my estimated slope parameter here? What is beta hat 1? Yeah, 0.07569. Yep. So it's this number right there. You don't have to write all those decimal points out. So to interpret this, anybody want to try interpreting that for me? Matt, give it a go.
1 degree increase in temperature, there's a 0.7569% efficiency removal.
Yeah, so for each 1 degree increase in temperature, removal efficiency increases by 0.07569. So that's excellent. There's one thing missing from that interpretation. Does anybody know what that is? Oh, so you could put you could put 7 point. I guess you could do it that way. Yeah. Yeah. So again, the key here is that this is what we would expect. So again, remember the linear model is it's y equals beta 0 plus beta 1 x plus an error term, and so we expect that error to be we expect that error to be 0. So this is just the interpretation is that we expect our y variable to increase by that much. So or you could say on average it will change by that much, or the expected removal efficiency will increase, but yeah, so that's important. We want to make sure that's an expected increase there. But very very good. Okay. So then, what is a 95% confidence interval for beta 1? Well, again, it's remember the confidence interval is an estimate plus or minus a critical value times the standard error. So what is that in this case? So what's my estimate for beta 1? Oh, that's beta hat 1. Come back to the critical value. What's the standard error of beta 1? Beta 1 hat rather. Yeah, so again, it's that number right there, 0.007046. And this is a good practice. What critical value do I want here? $1.96. Very nice. Yeah. Why'd you say 1.96? It's the best guess, right? So again, we'll use a z critical value here because the distribution of beta 1 is going to be a normal distribution. So that's something we talked about back in chapter 12. So we have a normal distribution going on here, which is why we'll do that. And so then my confidence interval is 0.0619 up to 0.0895. Does that confidence interval support our results from part C? So part C told us that there is a significant linear relationship between these two things. So if this is my confidence interval for beta 1, does that support that claim?
Yes.
Yes. Why?
Because it's positive, which means there's an increase.
Yeah. So there's the interval. The interval is completely positive, right? So this doesn't include. Sorry, that's bad. The interval doesn't include 0, so again, you're estimating that parameter is not 0, which does indeed support. That's sort of the same. Tells you the same thing as the hypothesis we checked previously. Very good. Okay. Party, I'm just asking you to look at some residual plots. Bottom line is, well, you could look check the solutions there. The residual plot and the actual versus predicted, they both look really good, and the normal probability plot's pretty good too there. So both of those assumptions would be okay here. So I'll skip over that for now. Yeah, Kevin.
If your interval includes 0, is there something more to say back? This one does suggest and this one doesn't, or just leaving it at that?
So if the interval did include 0, would you say something? Well, yeah. So Because it does support the results, that's fine. That's all you need to say. Yeah. So if it did include 0, then you'd want to go back and check your other answer, because that would be a contradiction itself. Yeah. So again, the point is that the F-test and the T-test for that involves beta 1 will tell you the exact same thing. They're equivalent results. Yeah. Okay. Well, I think this is a good place to stop. Let you guys out of here a little bit early. Thank you guys so much for a good semester. Hope you've enjoyed the class. Good luck and stay in touch. We'll see you guys on Thursday.